After studying this module, you shall be able to understand the concept of regression and prediction, differentiate correlation from regression, learn the method for making predictions, understand the regression model and the regression coefficients, understand the assumptions required for using the regression equation for prediction, and identify the situations in which one can apply regression. Introduction. The method of correlation helps us to understand the relationship between two variables statistically. By correlating two variables, a statistician can also forecast about one variable by studying the other one. In statistical parlance, this process of forecasting one variable upon cues from the other is called prediction, or regressing one variable upon the other. The essence of the process of regression analysis is establishing relationship between the variables and then predicting the dependent variable from the other variable, that is the independent variable. Regression and prediction. Need for prediction. Uncertainty is something that is difficult to handle. For instance, waiting for the announcement of the winner of a reality show for a television viewer. To confidently predict the winner of the reality show, one needs to know first what factors will guarantee a particular outcome. One way to do this could be to collect data and use this data to predict the evaluations of the contestant's position. This understanding could take into account some variables like the quality of performance by the actor in the show, the age of the performer, the appearance and behavior of the actor, as well as the audience watching the show. A regression analysis with this data would enable one to make predictions about future evaluations like the prospective winner in the future reality shows based on values of predictor variables. If, for example, physical attractiveness was an important factor in getting a good viewer evaluation, then another contestant could, through his or her looks, try his or her luck in the next show, or if behavior was influential, then one could bank on his or her interaction with the co-contestants. Similarly, in psychological research, one finds instances where correlated variables like IQ, that is the intelligence quotient, and academic achievement, that is the two being positively correlated, IQ and academic achievement, can be used to make predictions of one from another with more than chance accuracy. If found that IQ and academic achievement share a high degree of relationship, then it is easy to predict about the chances of high academic achievement of a person who has a high IQ score. The closer the relationship any two variables share, the better and less erroneous the predictions are. Of course, one needs to fit in a model to describe the relationship and then go for prediction of the outcome on the basis of the independent variable with some component of error involved. The predictor can be a single variable, which we call as simple regression, or a number of predictors may also be used, and when there are a number of predictors used to predict a variable, then we call it as multiple regression. So, a regression is something like predicting the outcome by fitting a model with some degree of error involved in it. The need for regression. As studied in the module on correlation, the relationship between two or more variables can be measured by the concept of correlation in statistics. Working further on it, if one wishes to predict one variable from another, regression becomes a useful concept to be put into use. For instance, if the researcher wants to predict the level of candidates' quickness in responding to an employer's questions from the amount of time one has slept the previous night, he or she would expect a positive relationship. That is, more the amount of sleep, quicker the responses. The basic relationship could then be extended to answer a question like, if a candidate has slept for two hours, how alert would she or he be? This is the foundation of regression analysis, where a model is fitted to the data and then it is used to predict the values of dependent variable from an independent variable. History of regression. The term regression was first used by Francis Galton in 1886 with reference to the inheritance of stature. He found that children of tall parents tended to be less tall, whereas the children of short parents tended to be taller. Thus, the heights of the offsprings tended to move towards the mean height of the general population. The tendency of maintaining the mean value was called the principle of regression by Galton. And the line describing the relationship of height in parents and offsprings was called the regression line. Thus, the predictor variable here becomes the parent's height and the outcome variable is the child's height. The prediction of one variable from the other is the concept of regression. Similar to correlation, regression is used to analyze the relationship between two continuous variables. It is also better suited for studying functional dependencies between factors, that is, where x partially determines the level of y. For instance, as age increases, blood pressure increases, but the length of arm does not have an effect on length of the leg. Also, it becomes better suited than correlation for studying samples in which the investigator fixes the distribution of x or the predictor variable. Let us study the simple linear regression. What is simple linear regression? A simple linear regression model includes one explanatory variable, that is the independent variable, and one explained variable, which we refer to as the dependent variable. For instance, as shown in figure, if one intends to see the effect of hours of study on the levels of achievement in an exam, thus hours of study becomes the independent variable and the dependent variable is the level of achievement that would be there for the students. Placing the independent variable on the vertical y-axis and the dependent variable on the horizontal, that is the x-axis, we take a graph. Taking 50 cases of hours of study and student performance, a scatter plot is constructed to show the distributions along with the line of best fit. That indicates the relationship between the two variables. The line of best fit is the closest straight line which can be made to account for variance in the scores and aims to have the same number of cases above and below it and each point as close to the line as possible. So, some scores might be very close to the line and the others might be at some distance. You can have a look at figure to observe this scatter plot, that the greater the number of hours spent in studying, the greater is the level of achievement. The line of best fit is indicative of a positive relationship and a strong one, as the slope of the line is quite steep with respect to correlation. But regression can predict the value of amount of one variable when value of the other variable is known. And as can be seen, if one studies for 2 hours, the level of achievement could be 43 marks out of 70. For 4 hours, it would be 72 marks out of 80. We can do this by dropping perpendicular on relevant points from the line of best fit. Simple regression can be used to calculate the values that are within the limits of the actual line and not beyond it. One cannot predict outside the limits of the line. The distance of the data points from the line is termed the residuals. Where the line strikes the y-axis, it is termed as the intercept, and as can be seen, the line does not go through the origin but starts a little way up the y-axis. Linear model and regression. In a scatter plot of two variables, there are several lines that could be used to explain the fit in the data. Readers would recall them as the lines of best fit. This line describes the general trend in relationship between the two variables. For being able to make sure and accurate predictions, one wants to fit a model that best describes the data. Therefore, a mathematical technique called the method of least squares is used to establish the line that best describes the data collected. The method of least squares finds a line that goes through or as close to as many of the data points as possible. Out of all the possible lines that can be drawn, the line of best fit is ascertained, which results in the least amount of difference between the observed data points and the line. But whichever be the line of best fit, there will always be small differences between the values predicted by the line and the data that was actually observed, as indicated in figure. We can see the red dots that are data points which are away from the line of best fit, right. The straight line becomes our model, which is used to predict the values of y from the values of x variable. This straight line assesses the fit of the model by looking at the deviations between the model, which is largely the mean model and the actual data collected. The mean model is the simplest model available because on an average it will be a fairly good guess of an outcome. These deviations are the vertical distances between what the model predicted and each data point that was actually observed. The differences mentioned here are called residuals. The data points fall both above, which show the model underestimates their value, and below the model, which shows that the model is overestimating the values, resulting in both positive and negative deviations or differences from the actual point. Since these differences cancel each other, on summing them up, the differences are squared to overcome this problem. The squared differences give an assessment of how well a line fits the data. If the squared differences are large, the line does not represent the data appropriately, and if the squared differences are small, the line represents the data well. The line with the lowest squared differences is the line of best fit or the regression line. The regression coefficients. A straight line has two important terms associated with the intercept and the slope as indicated in figures 3 and 4 respectively. The slope is the gradient of the line denoted by B1, and the intercept is the point at which the line crosses the vertical axis of the graph, and it is denoted by B0. The equation for the model thus becomes y equal to B0 plus B1 x1 plus error, that is E, where y or yi is the outcome one wants to predict, x1 is the ith participant score in the predictor variable, B1 is the gradient of the straight line fitted to the data, B0 is the intercept of the line, and E is the residual term representing differences between score predicted by the line for participant I and the score that the participant I actually obtained. B1 and B0 are known as the regression coefficients, representing the gradient of the regression line. The value of B represents the change in the outcome resulting from a unit change in the outcome. The gradient tells us about the nature of relationship between the variables, and a line having a gradient with a positive value suggests a positive relationship, while a line with a negative gradient describes a negative relationship as shown in figure. The intercept tells us about the location of the model in the geometric space. These values can be used to describe one's model. Therefore, using the regression equation, one may find the line of best fit, then one can estimate the gradient and the intercept of that line. These different values of predictor variable can then be inserted into the model to estimate the value of outcome variable. A regression coefficient of 0 implies that when there is a unit change in the predictor variable, there is no change in the predicted values of the outcome and gradient of the regression line, as 0 implies that the regression line is flat, and therefore, if a variable significantly predicts an outcome, then the B value should be significantly different from 0. This can be ascertained using the T statistic also, that tests the null hypothesis of B is 0, and hence we gain the confidence that the predictor variable significantly contributes to our ability to estimate the value of the outcome. The equation to calculate the T is T is equal to B observed minus B expected upon the standard error of B, where B expected is the value of B we would expect to obtain if the null hypothesis is true, which is hypothesized to be 0. The standard error of B is calculated by plotting a frequency distribution of the B values of many samples and computing a standard deviation of this frequency distribution as a measure of similarity of B values across the samples. The degrees of freedom in regression are n minus p minus 1, where n is the total sample size, p is the number of predictors, and one can find out the exact probability of the observed value or a larger value of t would occur if the value of b was 0. If this observed value of t is significantly less than 0.005, then one can assume that b is significantly different from 0 and the predictors make a significant contribution to predicting the outcome. Applications and assumptions of regression. Applications of regression. Regression method can be applied to seek some sort of descriptive relationship between a set of measured variables, like sociologists wanting to establish a relationship between the occupational status of an individual and the educational level of the person as well as his or her parents' educational level. Then, to provide evidence for a theory, for instance in estimating the coefficients for an established model employed in relating a particular plant's weight with the amount of water it receives, available nutrients in soil and sunlight it is exposed to. It can also be used to predict some response variables at a certain level of other input variables which play a role in planning, monitoring, altering or evaluating a process. It can be used in the areas of demand management and data analysis in the field of business, social, psychological or any research of any field like agriculture to predict the yield of a crop, for instance by studying the role of quality of seed, soil fertility, temperature, rainfall, etc. and of course the widespread application in the field of behavioral sciences too. Assumptions for regression. The linear regression demands several assumptions to be fulfilled by the data before it can claim to give accurate results upon its applications. Some of the key assumptions are that the relationship between the variables should be linear. This simply means that relationship between the two variables being considered for simple regression can be described using a straight line. This assumption can be easily checked by drawing a scatter plot. The normality. Whenever a researcher wishes to use the regression line for the purpose of prediction, it should be made sure that the distribution of the variables x and y are normal. If the distributions deviate from normality, then the skewness should not be very high. The assumption of normality in bivariate distributions can be checked using the graphical method of histogram. The homoscedasticity. The homoscedasticity refers to uniform spread or scatter of scores throughout a distribution. It is assumed that the estimated or the predicted values are scattered uniformly around the observed values for all the observed scores of the distribution. This enables the researcher to use a uniform or same measure of spread, that is standard error of the estimated variable. To put in other words, one may assume that the range of permissible fluctuations in the predicted value of the variable are same for all the observed value. The scatter plot is a good way to check whether homoscedasticity, that is the error terms along the regressions, are equal. As the assumptions discussed are satisfied by the data set, the researcher can be assured that the predictions of the variables upon the others would be less fraught with errors and more reliability in the results can be ensured. Summary. The text can be summarized as, by correlating two variables, a statistician can also forecast about one variable by studying the other one. In statistical parlance, this process of forecasting one variable upon cues from the others is called prediction, or regressing one variable upon the other. The closer the relationship any two variables share, the better and less erroneous the predictions are. Of course, one needs to fit in a model to describe the relationship and then go for prediction of the outcome on the basis of the independent variable with some component of error involved. The predictor can be single, as in simple regression, or a number of predictors may be there, then it is called the multiple regression. Out of all the possible lines that can be drawn, the line of best fit is ascertained, which results in the least amount of difference between the observed data points and the line. But whichever be the line of best fit, there will always be small differences between the values predicted by the line and the data that was actually observed. These deviations are the vertical distances between the model predicted and each data point that was actually observed. The differences mentioned here are called the residuals. A simple linear regression model includes one explanatory variable, that is the independent variable, and one explained variable, that is the dependent variable. Simple regression can be used only to calculate the values that are within the limits of the actual line and not beyond it. One cannot predict outside the limits of the line. The slope is the gradient of the line denoted by B1, and the intercept is the point at which the line crosses the vertical axis of the graph, which is denoted by B0. The equation for the model thus becomes y equal to B0 plus B1 x1 plus error. The assumptions required to be met for the regression line for prediction purpose have also been discussed in the text along with the applications of the regression.